Okay, hello everybody. It's a great pleasure to introduce Gianni Maso from SISSA. Before we start, I will say a few words. So Gianni graduated from the University of Pisa and got the diploma from Scuola Normale, where he was also a PhD student under the supervision of Colloquio De Giorgi. He has been assistant professor in Udine before joining SISSA as an associate professor first, and then as a full professor. So he has been head of the functional analysis sector, vice director of SISSA, and coordinator of the mathematics area. He supervised more than 40 PhD students and I guess an uncountable number of postdocs. He got several recognitions, including the Stampacchia Prize, the Cacciopoli Prize, the medal from the Accademia Nazionale delle Scienze, Premio del Ministro per i beni e le attività culturali, awarded from the Accademia Nazionale dei Lincei, and the Luigi and Wanda Merrior Prize. He's a fellow of the Istituto Veneto di Scienze and of the Accademia Nazionale dei Lincei. Other appointments include the scientific committees of the Italian Math Union, CIME and NIAMPA, where he's now director. And he is also in the editorial board of several renowned mathematical journals, and he has been invited professor at several prestigious universities in Europe, US, and Asia. His research activity mainly regards calculus of variations, and he obtained fundamental results about semi-continuity, relaxation, gamma-convergence, and more recently to problems with free discontinuity and applications to mechanics. And he will talk about homogenization of free discontinuity problems, the vectorial case.
Thank you. Thank you very much for this introduction. So I'm really honored to give a Colloquio De Giorgi, because you know that De Giorgi was very important in my scientific formation. And I am very glad that essentially all the results that I will present come in one way or another one from ideas developed by De Giorgi, starting from the first line, homogenization. So homogenization and the use of gamma convergence for the study of homogenization problem was something that was introduced by De Giorgi during the 70s and the 80s. And from the end of the 80s to the end of his life, he also worked in free discontinuity problems, and really the name is due to De Giorgi. So let me start with my own view about free discontinuity problems. So these are minimum problems which where we have a volume integral, as in the usual problems in the calculus of variations, that is summed to another term that is a surface integral, and the surface is the discontinuity surface of the unknown function u. So the difficulty to deal with these problems is that this discontinuity surface itself is unknown. So today I will consider functionals of this form. You see on the left we have the volume part. And so here my notation will always be the following. A is bounded open set in Rd. The function u that we consider is vector valued, is a function from the set A to some Euclidean space Rk. Ju is just the jump set of this function that we will assume is a set of codimension 1. So the dimension d minus 1. Then these brackets denote the amplitude of the jump, which is defined as the difference between the limit on one side and the limit on the other side. And as we shall see, it is possible to define these notions of limits in a suitable weak sense. So this will be a function from the jump set with values in Rk, and then nu is the unit normal to the jump set, and h d-1 is, as usual, the d-1 dimensional Hausdorff measure. So I'm interested mainly in applications of this theory to fracture mechanics, and in this case, the function u represents the displacement of an elastic body subject to fracture, and ju represents the crack in the reference configuration. So I have to say that there are several functionals that can be used for the purposes of fracture mechanics, and I divide them into two large classes. So one class is the class of what I call the brittle fracture models. In this case, the surface term G is bounded away from zero. The infimum is strictly positive. What is the mechanical meaning in terms of when we apply this to fracture mechanics? Is that when we have to produce a new portion of the crack, we have to pay a given amount of positive of energy that is proportional to the area of the added crack. And so this quantity is at least this infimum of G. And so a typical example is the simplest case where G is identically 1. And this model has a name, is the Griffith model. That was introduced, of course, not with this kind of notations, by Griffith 1 century ago. So the idea is that in that model, the energy that you spend to produce a new crack is proportional just to the area of the new crack, and the proportionally constant here, I'm assuming it is equal to 1. So the cohesive models are different because in this case, this infimum is 0 because the function g takes the value 0 at 0, but not in a discontinuous way, but in a continuous way. Indeed, there exists this directional derivative, and it is finite. So not only it is 0 at 0, but essentially it is proportional to the size of z when z is very small. And so the typical example here is you take the norm of the amplitude of the crack and you truncate, for instance, at the level 1. And so here, what happens is when you want to produce a new portion of crack, in the case where the opening is small, then you pay an energy that is proportional not only to the area of the crack, but also to the amplitude of the crack. To be precise, it is proportional to the norm of the amplitude of the crack. And the proportionality constant is given by this sort of derivative computed at the normalized direction corresponding to the opening of the crack. And so this depends, of course, on the location, on the direction of the opening of the crack, and on the normal to the crack set. And so from the point of view of mechanics, since you have that the energy that you spend to produce the new crack is the work done by the force that acts between the crack lips. And since this force now is proportional to the size of the crack opening, this energy is proportional to the size of the crack opening. This means that for small values of the amplitude of the crack, there is a well-precise force. Which is given by this proportionality coefficient. This when the crack has a very small opening. And of course, so this explains the name cohesive in the sense that you don't have a brutal opening of the crack that so you just spend some energy to open, but then you don't have any attractive force. Here, at the beginning of the process, you have to counteract some force. And then, of course, for large values of the opening of the crack, the force will be zero. And so this is reflected by another assumption that we have to make on G, that is to say that this energy density due to the surface term is constant for large values of the opening. So at the end of the story, this function G, the natural assumption from the point of view of fractal mechanics is that it is bounded. Now, how to deal with minimization problems for this kind of functions. So let me begin. The story is very long, of course. The point is that, first of all, you have to study this problem in a space of functions that admit discontinuity along sets of codimension 1. And the most natural choice is the space BV of functions from A to Rk, which is defined as the functions that are in L1, whose gradient in the sense of distributions is radon measure. And when we take a function in BV, we can decompose its gradient, that is a measure, into its absolutely continuous part with respect to Lebesgue measure and the singular part. The singular part can be further decomposed into two parts. One that I denote by dj is the part that lives on the jump set. It's just the restriction of the measure du on the jump set. And then there is a residual part that is called the Cantor part, which is singular, but it is supported by some set that is different from the jump set. And so it's an object that has a sort of intermediate dimension, because the absolutely continuous part you can consider has dimension d. The jump part has dimension d minus 1, and this is something in between. Just to make clear what is written in the rest of these slides, nabla from now on is just the density of the absolutely continuous part. So this is well defined, is a function of class L1 with values in a suitable space of matrices. The jump set, the jump part, it is known that it has an elementary representation in terms of the amplitude of the jump and of the normal to the jump set. You simply consider the tensor product of these two vectors and you multiply it by the Hausdorff measure on the jump set. Well, the counterpart is something that is in some sense out of control, and we know that for some functions it exists, because if you take the Cantor Vitali function, which is an example even in dimension 1, you have that in this function, the absolutely continuous part is 0. The jump part is also 0 because there are no jumps, but the function is not constant, so the derivative is not 0. And in this case, the Cantor part coincides with the full derivative. Oh, now, when we consider the problems that I called those of the brittle model, where the infimum of the G is far from 0, then it is possible to study these problems in the space of functions that have no counterpart. So this was called the space of special functions of bounded variation. And by definition, it's just the space of functions that are bounded variation and such that this nasty counterpart is 0. You can study the problem in this space because of a very important theorem due to Luigi Ambrosio, and also the job was announced together with De Giorgi at the end of the 80s, which ensures that under some conditions you have that you have a compactness result. So the conditions that one important condition is that the measure of the jump set, the d-1 dimensional measure of the jump set, must be uniformly bounded. So if you take a minimizing sequence for this problem, since the infimum of G is strictly larger than 0, then if you look at the formula, you see that you can write along the minimizing sequence a bound on the Hausdorff measure of the Hausdorff measure of the jump set. And then this allows you to apply this compactness result and to say that you get a limit that is still in the same space, because this is the important point, because in general, if you start from a sequence of SBV functions, the limit, if it exists, it could be maybe a general BV. But not in this case. So for these brittle problems, this is the good space. In the cohesive case, the problem from the mathematical point of view is totally different. The main difference is due to the fact that now, since the infimum of G is 0, you even have this derivative that is a finite everywhere. You have that along a minimizing sequence, you cannot control the size of the jump set, so the d-1 dimensional measure of the jump set. So we cannot apply the compactness theorem in SPV. And so the only possibility seems to be, why don't we try to study the problem in the larger space BV, and maybe take into account also the counterpart. And indeed, you have to take into account the counterpart, because when you want to apply the direct method of the calculus of variations to this problem in the case of BV, then you need semi-continuity with respect to the Wistar topology in BV. And well, there are some conditions that imply this lower semi-continuity. Now, I have to be quick, so I cannot say exactly what they are, but I can say that there is also a relaxation theorem that says that if you start from a function in this form and you relax it because it is not lower semi-continuous, you can take the lower semi-continuous envelope, what you get is necessarily a functional that contains three terms, one for the volume part, one for the Cantor part, and one for the jump part. So in the best situation that your original problem was lower semi-continuous, you cannot avoid this term because this f infinity is not an arbitrary function, but it is exactly the session function connected with f. So if f is non-trivial, also f infinity must be non-trivial, and so you have to deal with the counterpart. So this is, if you want, one of the first difficulties. But there is a second difficulty, that is that if you now admit that we have to study this kind of functions, we have to enlarge it and to take into account also the counterpart. But the problem is that along a minimizing sequence, in order to apply some semi-continuity result in BV, we need to control the BV norm. And this is also not possible because of the following reason, that if you take a minimizing sequence for this function with three pieces, you, on the one hand, can control the nabla in L1, because if you can assume that f is coercive, then the first term controls the L1 norm of the absolutely continuous part. You also control the total variation of the counterpart, so also this is fine. But what you cannot control is the jump part, because you cannot control the amplitude of the jump. And this is due to the fact that in the hypotheses that are relevant for fracture mechanics, G-bounded, you cannot have a bound from below like this, because this bound from below would help, because of course if the functional is bounded, if the sequence makes the functional bounded, then you have that the L1 norm of the amplitude of the jump on the jump set is bounded, and then you have a bound on the jump part. But this is not what happens in the interesting problems. And so now, unfortunately, we have to go beyond BV, and one possibility would be to consider the space GBV that also was introduced in that years that I mentioned before about these theorems. But GBV is what? Is the space of functions whose truncations belong to BV. But there are two difficulties, to mention only the most important ones. So one is that for GBV, it is not at all clear how to define the counterpart, because GBV, even the gradient of U is not well defined. And so you cannot have the decomposition. And so, and then there is another point that could seem technical, but it is very important, is that GBV is not a vector space. And so now here we need a suitable subset of GBV that is a vector space and that allows us to define the counterpart. And we called this space GBV star, for lack of other names. So this is a variant of GBV. And it is defined in the following way. You take all functions such that when you take a component, a scalar component of this function, and then you truncate it in this way, you get a function that is BV, and in addition, you want a uniform bound for these terms, the nabla term, the Cantor term, and a part of the jump, not the whole jump part, but only the truncated jump part. These are this is the assumption which defines the space GBV star. I studied this space in the scalar case together with Rodica Toader, and now my student Donati has extended almost all of these results to the vector case, starting with this definition that seems suspicious because in some sense it seems that it depends the coordinate system, but you can prove that this is not the case. If you rotate and so on, you remain in the space. So this is just to give the simplest possible definition, but this does not depend on the coordinate system. So what we can do with this space is that we can define a measure that has the role of the Cantor part, by taking the limits of the measures that appear in these truncations. And this can be done even if the full gradient is not well defined, because this function u is not even to assume to be in L1, so there is no, we cannot apply the standard theorem of distributions. But in any case, this counterpart can be defined, and also we can prove that this space is a vector space, which is useful in a lot of technical points. So this seems to be the best space to study this kind of problems. Yeah, but now I want to pass, because of course I could continue now to say you have a single problem, what are the conditions that imply existence of a solution, because now I said I prepared the space, but you have to deal with lower semi-continuity issues, some compactness result. But I prefer to give just the result for the homogenization problem, and not just for the minimization of a single function, but consider a sequence of functions. So homogenization means that we want to consider a model to study composite materials that are highly inhomogeneous. Suppose that they are formed by several grains, and when the size of the grains tends to 0. And the idea is that when this length scale that is called epsilon tends to 0, what you expect is that instead of a highly heterogeneous material, you have an effective homogeneous material that describes what happens when epsilon is small. So this homogenization problem was studied a lot during the 70s of the last century, and De Giorgi proposed to use gamma convergence to study this kind of problems, also in the case where it is not easy to write the Euler equation, just a sort of a direct variational approach. So in our case, so when you study this homogenization problem, the standard idea is you replace epsilon by x over epsilon, so you change scale essentially, and you want to determine what happens when epsilon tends to 0. And since our problem are variational problems, you have to study the limits of these functionals when epsilon tends to 0. Of course, the first line refers to the brittle case, where the problem is obtained, the minimum problem is obtained using that functional in the space SBV, while in the the cohesive case, you have to deal with this more difficult functional in this space GBV star. So the common problem is what is the limit as epsilon tends to 0 in the sense of gamma convergence. And here gamma convergence is studied with respect to the convergence in measure for what refers to the functions u, because there is no other topology for which the displacements are compact. So to anticipate the result I'm going to report, I will say that in the brittle case, we have separate effects of the volume part and of the surface part. That is to say, when we will write the limit functional, it will be a functional with an F homogenized and with a G homogenized, and the F homogenized depends just on F, and G homogenized depends just on G. In the cohesive case, things are different in the sense that at the end of the story, we shall see that the gamma limit will be still a function where there will be a F homogenized, its recession function, and a G homogenized. But this time, F homogenized depends both on F and G. And G homogenized also depends on both. So there is interaction between the two terms. So this is a more challenging problem. So now I can say what are, no, it is difficult for me to give a complete list of all hypotheses because yeah, they depend, but just to give the main ideas and the main hypotheses. So in the brittle case, now I will be more precise. So we assume that our F is with P growth, which means controlled from above and from below by Xi to the power P. And this P is supposed to be larger than 1. G, as we have said, in the brittle case is far from 0, so it is larger than a constant, larger than 0. And I said that from the point of view of mechanics, it should be bounded. But some results can be obtained if you relax this condition, and instead of a bound from above, you consider that it is bounded by something that is linear in the amplitude of the jump. Now, I need some notation that will be used also for the cohesive case. So Q x rho is just the cube with center x, radius rho, with the sides parallel to the coordinate axis. While Q ni will be a cube with the same side length equal rho, center x, but now it is oriented like ni, in the sense that one face is orthogonal to ni, and a pair of faces of opposite faces is orthogonal to ni. All other faces are parallel to ni. Then, just to simplify some formulas, I use this symbol LXI for the linear function with gradient equal to Xi. So it's just Xi times X. Oh, this is the pure jump function. So it's a function that jumps from 0 to zeta along a planar interface. More precisely, it depends on all these parameters. So zeta is the amplitude of the jump. You go from 0 to zeta. And this, the interface is the hyperplane orthogonal to me passing through x. So you consider this special function that plays an important role in this theory. And now I can describe the two separate problems that we shall use for the volume part and for the surface part. So for the volume part, I consider as a target this function with a linear function with slope equal to xi. And I simply minimize the volume term in the usual Sobolev space, in the sense that the Sobolev space W1P with boundary condition equal to this linear function on the boundary of this cube. So in this case, so the problem is a classical one. There are no jumps in these problems. Is a problem in the Sobolev space. For the surface part, I try to do something similar, but as a boundary condition, I consider this a pure jump function. And now I minimize just the jump, the surface part. And among all possible functions that are piecewise constant, and take on the boundary of this cube the boundary condition that is given by this. So in half of the boundary we have zeta, and in the other half we have 0. This problem has no solution in general, it's just an infimum, but this determines an object that is relevant in the homogenization formulas. Now come the theorem that requires a lot of comments and explanations. So our idea was to find what are the most general conditions to have a homogenization formula, even without periodicity assumption with respect to x, because for those that started their careers studying homogenization, they know that in general the first case we study is the case where these oscillations are periodic, and in this case some formulas are simpler. But the problem is that now our aim was to study similar problem in the case of stochastic homogenization. In the case of stochastic homogenization, it is not true that almost every realization is periodic. This is completely false. And so we have to be able to homogenize also non-periodic functions. And so what we have to assume is the existence of these limits. So what is the first one, for instance? So I consider the matrix Xi. Then I consider the linear function that has as a gradient. And then what I do is I solve the minimum problem in a large cube, because the cube has a center at rho x, radius rho, and rho is going to infinity. So the cubes are larger and larger. And I normalize this by the size of the cube using the standard volume normalization. And I'm assuming that this limit exists and is independent of x. So, of course, here the big question is when is this satisfied? So I can anticipate that. So this is a reasonable assumption, because in the periodic case, this is true. So this we know. And we shall see that because of some probabilistic theorem that I will apply later, this is true in almost every realization of the problem that leads to stochastic homogenization. So for this reason, this is quite a natural assumption. And we have to do something similar for the term corresponding to the surface. So this term here we consider these larger and larger cubes. Now they have to be oriented according to this knee. We consider the minimum problem among piecewise constant functions that at the boundary take the value of this pure jump function. And also here the assumption is that this limit exists for every x and that it is independent of x but depends just on z and c. The conclusion is that in this case the functionals that we cannot consider them exactly in SBV, but we have to consider also this a little bit extended in GSBV, so the functions whose truncations are in SBV. In any case, there is never counterpart here. Well, these functions gamma converge when epsilon tends to 0 to a functional that is more or less of the same form, but there is no dependence on x, as you expect in the homogenization limit. But more than this, you can say that the integrands that appear in the homogenized limit are exactly those that were obtained by considering these limits on large cubes. And this is the key then to apply probabilistic result and to deal with the stochastic homogenization. Now, there was a part that I will skip because after that we studied a problem in BV where we have the three terms including the counterpart, but this time we have a control from above and below of G by the modulus of Z, which, as I said, is unnatural because G must be bounded. And so this was just to warm up to see what happens in that case. So I will not tell you the result. Now let us see what happens in the interesting case, so the cohesive case. In the cohesive case, as I anticipated, in order to have a lower semi-continuity and other problems like that, we have to assume that F has linear growth. So now, this time P is equal to 1. And our G is of cohesive type in the sense that it is controlled from above and below, not by means of modulus of Z, but of the truncation of modulus of Z. So in particular, it is bounded from above. And then we assume that this limit exists because this is an important part of the theory. Now, what we consider, since this functional is very long, I give a concise name to it. So this is an energy that depends on F and G. And for technical reasons, I will be interested in the same functional with F and G replaced by G0, where G0 is this limit, or in some other cases where F is replaced by F infinity and G remains G. And so, more precisely, when we consider the problem that we shall use to determine the homogenized expression for the volume part, we have to deal with this functional corresponding to F and G0. And we have to minimize it with boundary condition equal to this linear function. So this is the condition on the boundary. But we have to consider the full functional with the three terms, not just the volume term. And then there is an additional complication due to the fact that for some reasons we have to make this difference bounded. So it depends also on another parameter. But fortunately, this can be included easily in the results. And for the case that when we have to deal with jumps, we do something similar, but this time we are minimizing the function that corresponds to f infinity instead of f and the true g. So in some sense, yeah, when we want the volume part, we can modify a little bit g, and when we want the surface part, we have to keep g as it is, but we can modify f. And the boundary condition is this special function, and so on, and the problem has to be studied is the infimum in BV. Now, the results that I have obtained with Rodica to other in the scalar case, and now we are writing the final version of the vector case together with Davide Donati, which is my student, my PhD student. And so now the hypothesis is parallel to the one that we considered for the brittle case. So we assume that for every x, we have that these limits on large cubes exist and do not depend on x. The only difference is that before the problems for the volume part depended only on the volume part. Now they depend on both, and the same for the surface part, because you see here it depends not only on G but also on F infinity. And so it is natural that in the case of the volume, you rescale by rho to the power d, while in the case of the surface, the rescaling is with d minus 1. In here, what we have that if these limits exist, then the problem is homogenizable in the sense that it gamma converges as epsilon tends to 0 to a functional that is similar to the one that we considered before. There is no x gain, and the integrands are exactly those that are described in this strange theory. Also here we can say that if we are in the case where the starting f and g are periodic with respect to x, then we are sure that this limit exists and do not depend on x. Now, just I want in one slide to say what are the main difficulties that we have to face. So first of all, this first sentence is homage to De Giorgi. So the idea is that in order to prove these results, we use the standard gamma convergence approach. So we have that due to suitable compactness theorems that are very general, there is a subsequence that gamma converges to something that depends on, you do this on different open sets, it depends on X and U. And then the point is to say a lot of properties about this E that lead to the fact that this limit can be represented exactly using this F-hom, G-hom, and so on. But in the case that I omitted, where the problem was with linear growth both in F and G, then a key result was a result by Bouchité, Fonseca, and Mascarenhas that says that under some assumptions on this E, U, and A, that you may imagine, lower semi-continuity in respect to one variable, the fact that it is a measure with respect to the other variable, and so on, we can represent this as the sum of the three terms. And these are also determined by considering some limits on small cubes. Here, the problem is that, first of all, this is a theorem that was proved in BV. And now we are working in a larger space. So we have at least to extend this result to the larger space. The other difficulty is that the starting point of this theorem is that with respect to A, this is a measure. And so are we able to prove this in the new setting? And yeah, the answer at least yes, but it is not immediate. And another point is that in order to pass from the representation in BV to the representation in this larger space, you have to use suitable truncations. In the case of scalar function, the truncation is a standard one. So you truncate some constant level and then you send the constant to infinity. In the new case that I'm studying together with Donati, when we are in the vector value case, we have to adopt a different form of truncation. Sort of smooth truncation is a composition U with some functions that are the identity in a ball of radius m, and then they send everything to zero in a much larger ball. But you need good estimates in order to obtain that at the end of the story you can approximate in this way. And then this is the hard part that fortunately was done. So now I can pass to the stochastic homogenization. So the standard way to deal with the stochastic homogenization problem is to consider a probability space and a group. Here I prefer the case where the group is indexed on Zn, on the integers to the power n, of p-preserving transformations, which means measurable mappings from omega to omega, which preserve the probability. And now we have to consider integrands that depend also on this probabilistic variable omega. And we consider those that are stochastically periodic, in the sense that if you translate the variable x by an integer, the result is the same as applying the group of transformations to omega. This is the same for G. Usually in the probabilistic literature, this is assumed not only for Z integer, but for every real Z, translation of a given vector. And in this case, this is called the stationarity condition. I prefer to consider the weaker condition of stochastic periodicity, because I want to include in what I'm going to do also the case of purely periodic functions. So in this case, this means that omega is a singleton, the function is periodic, and then what I say for this stochastically periodic function in particular is valid for periodic function. Otherwise, if I want to transform a periodic function into a stationary stochastic process, I have some technical problems. Now, I have to say that if you remember that we consider some minimum values corresponding to this boundary condition and corresponding to some functions and also to some truncation, but don't read the part of the truncation because this is really just a technicality. And the same for what concerns the minimum problems for the pure jump function. And then we can consider these objects as defined on all possible rectangles. And then what is important is that this can be seen as a function of omega and of the rectangle. And it has a very important property that it is, for every omega, it is subadditive. because it is clear that if I minimize, if R is written as the union of some disjoint rectangles, in each rectangle I take the minimizer or an almost minimizer, then I glue them together and I get something that is in competition for R, and so I have the subadditivity. And the other point is that we have for this a formula that is analogous to this one. So if I apply the group to omega, is the same as translating R. This is obvious. And so this is what Colloquio and Krengel called a subadditive process. And they proved a theorem that says that when we have a subadditive process, there always exists the limit of the process divided by the size of the rectangle when the rectangles become larger and larger, go to infinity. So now let me see what happens. Let me show what happens in our case. So the theorem is, as usual, a probabilistic theorem. So it's not for every small omega, but for almost every. We have that the limits that before, you remember there was a hypothesis. Suppose that this limit exists, then everything is done. Now I can show that these two limits really exist for almost every, not for every omega, for omega. This is a consequence of the fact that as a function of the argument here, this is subadditive, and that you have the stochastic periodicity. Not only they exist, but in the theorem by Colloquio and Krengel, they underline also that the value of the limit do not depend on the center of these expanding cubes. So this is crucial. Without that, we could not conclude. And so, yeah, maybe now I simplified too much in the sense that it is true for the first that you have just to apply the subadditive ergodic theorem to the process described from the formula on the left. But what happens in the other one where you are changing dimension? And here life is more difficult because you can, first of all, consider the problem along a hyperplane. And then with some trick, you can pass from the problem in dimension d, because this is a cube in dimension d, to a problem in dimension d minus 1, because you can see that everything depends just on the intersection. Yeah, but this is not finished, because then you can change the orientation. You have to see that nothing bad happens and so on, because if you deal with this, then for each possible orientation, you have a set of Maso zero. You change that, but you have an uncountable family of orientations. There is no continuity around, and so on. So there is another trick that is very deep, and is due to Piatnitsky to deal with also this. And then, yeah, once you have these two results, these two properties for almost every omega, then for almost every omega, you have the conclusion of the previous theorem. So you have the Gamma-convergence. So now, of course, as I said before, the periodic case is included in this with the trivial probability space. So we can say that in particular, we recover what we could have obtained in the periodic case. One has to say also that in any case, you have for the homogenized integrants some asymptotic formulae with larger and larger cubes. Can we simplify them? Not always. in the sense that if you go back to the case where the problem for the volume depends only on the volume part, this can be simplified in the scalar case if F is convex. But the term for G cannot be simplified. In any case, you must have a sequence. So the only possible formulas for homogenization in this case are not what in the jargon of homogenization is called a cell formula with a single cell, but with an infinite expanding. Now, last slide. So since here we deal with stochastic homogenization, it is useful to understand what happens if the process we are studying is ergodic. In this case, ergodicity means that the group of transformation that is underlying the process is ergodic in the sense that all sets that are fixed for all terms of the group have a probability either 0 or 1. In this case, you can very easily prove that the functions g hom and f hom that we have obtained before are independent of omega. And so also this is the interpretation of this is interesting, that from the point of view of the limit behavior of these problems, you have that the true problem is probabilistic. But when epsilon tends to 0, you have that the limit problem is fully deterministic because the F hom and G hom do not depend on probability. So these results about stochastic homogenization were obtained in this setting. First, in the case that I have I mentioned before, so the case where you have a separation of volume of surface integral because we are in the brittle case. And of course, I have to say more that the same technique and the use of the subadditive ergodic theorem in this framework goes back to the paper I've written with Luciano Modica in 85, I think. Yeah, so the idea is that one. The difficulty here was to apply it in the new setting, and also this problem of the change of dimension, that you have something for the volume, but something also for the surface term. And also we have a result in the case where G, instead of being bounded, is between Z and a constant times Z. This is the part that I omitted in the presentation. But in that case, in some sense, the problem is a little bit easier because it's formulated in BV. But in any case, you have the stochastic homogenization result. But now we are glad to deal with the case where the bound from above is this one, which is the correct hypothesis for fracture mechanics. So thank you very much.
Thanks for the great talk. Is there any question?
Thanks, Gianni. So you consider the brittle case in which G is far from 0,
yeah,
and the cohesive case in which both G and F, let's say, grow linearly.
Yeah.
So is there any, say, mechanical reason to exclude the intermediate case in which, say, the material is elastic outside the fracture, say F is the square, but the jump part G grows, say, like the square root of the jump?
So if you have that the part G, the volume part, has an infinite derivative of the origin, I think that you can repeat what I said for the brittle case, because I'm not sure of all details, But the problem is that the theorems by Luigi are valid also in that case. And now I would have to check a lot of details, but I presume that if you have a uniform control on this G that says it is like the square root, and the F grows like P with P larger than 1, I presume that you can repeat. I'm not completely sure that you can really separate the effect, but almost, I'm almost sure because yeah, because I think that just for the sake of simplicity that we said, if it is far from zero, then a lot of estimates are almost for free, but otherwise you have to work also for that estimates.
Other questions?
Oh, thank you, Gianni. I wanted to ask. In the case of linearized elasticity, maybe using also your space GBD, do you think that's something like that?
I hope, because when we will finish this vector case with Donati, our program is to attack the case where everything depends just on the symmetric part of the gradient. So probably we have to say something more on this GBD space that I introduced some years ago. In particular, we have to understand whether the Cantor part can be introduced without additional assumptions. I think probably yes, but since I've not done the proof, I cannot guarantee.
So you are more optimistic on the brittle case compared to the cohesive case. So the brittle case might be easier.
The brittle case, the brittle case probably might be easier because the space, in this case, it would be the space SBD for which there is no generalization. So probably in that case, but I'm more interested in the cohesive case. But I think that probably it could be done. But now we have some experience on how to do smooth truncations for vector functions in BV, not in BV, but in this generalized space. And I hope that this will be useful to consider something similar in the BD case. Although there are some difficulties because the problem is that even the composition does not work. So we have to do something different using slicing and so on. But this is a challenge that we try to attack.
Any more questions?
Actually, two curiosities. So the first one is the space GBD. You define by truncation, right? Can you?
The space you say is
star.
Yeah.
Well, it's essentially defined by truncation.
Is defined by truncations, yes.
Can you define it also by taking test function that depends not just on X, but also on U? Somehow pretend.
We have never considered this problem. Might be, I don't know. Yeah, because now what we have considered is the fact that it could be defined. So the original and easier definition is truncate each single coordinate. Then after some work, you can see that you obtain the same if you consider smooth truncations of the whole vector. If you consider a test function depending also on U, I don't know, maybe it could be, but we have not yet considered that case.
The second question is the following. So did you, okay, in principle, one of the problem is that you could become larger and larger.
Yeah.
Okay, that's what you want to avoid. What you cannot avoid, just
In
by
fact,
putting a bound on the end.
you cannot avoid using the functional. So this is the reason why we consider the notion of convergence, just the convergence in measure. So the only point is that you want to be sure that the target function is finite everywhere. But except that, you have only you can say only something about the truncation, and if you want, you cannot say what is the size of the opening of the crack, but only of the opening truncated by some constant. This is.
Is there any chance that for minimizers somehow you know that they have to be? So what I'm trying to say, that one would say that a minimizer where U is really unbounded sounds, I wouldn't say unphysical because that's correct.
Yeah.
Something. So did you ever try to see whether you can somehow go around this problem by proving some a priori, whatever? Is that something feasible or simply easy?
I think that it could be a little bit difficult because I think that we have an example where we consider a problem. Suppose that instead of considering the homogenization problem, you consider just a minimization problem with prescribed boundary conditions. And if the boundary condition is in some Sobolev space, but it is not bounded in L infinity, I think that we have an example where you cannot obtain a solution in BV, but only in this space. And now maybe this is because we wanted too much to have even that the boundary condition is not in L infinity, but still, since we are dealing with BV, it should be natural that if the boundary condition is the trace of a function in the Sobolev space, you expect. So the problem is not so clear. So I cannot say, maybe with some good assumptions, maybe that the value that you prescribe at the boundary in some weak sense is also in L infinity. Maybe you have some way to circumvent the problem and to get a solution in the usual BV. But if you just replace L infinity by H1 half or something like that, the answer is no.
More questions? I actually have a qualitative one. So when you observe the cracks in materials, sometimes they are like smooth, like cuts, and sometimes they're very irregular. So is there any sort of general principle that determines the type of the crack?
A difficult question because now the point is that when you are considering what I call the brittle case, now, of course, by considering a very special term as F and so on, there are some regularity results for the minimizers. The point is that, unfortunately, from the point of view of fraction mechanics, the minimization of this is just what happens when you do discrete time approximation, and this is what happens at the first time, and then you have to repeat and so on. And so while there is a progress about the regularity of single problem, there is so far it is not for the quasi-static evolution, the results are not complete in the, say, in the brittle case. If you consider the other case, which is not brittle, Then here also there are some other questions like this posed by Giovanni that might be under some assumptions you can even avoid the counterpart. This is true, but not so. For instance, we have a really very partial results. So if this function g with a finite slope at the origin is strictly concave, maybe there is some hope that the counterpart does not appear in a true minimization problem. Although you have to consider it if you want to apply the direct method. But also this, unfortunately, there are no, so we made several attempts, but there is no complete result. Of course, if this G is really linear and then constant, probably you have no hope, the counterpart could be there. But there could be some natural assumption on G that could be relevant for mechanics and which would exclude the counterpart. Yeah, but this is a dream.
Thanks. All right, so if there are no further questions, we can thank Gianni again.
Thank you.